This is the lecture where we're going to start talking about free energy, one of the most powerful conceptual tools that we have in classical thermodynamics. But to get there, we're going to need to go through some mathematical machinery first, namely the Legendre transform, which is a function transform that you probably haven't seen before. You may be more familiar with the Fourier transform, which takes functions in, for instance, one real dimension and turns them into other functions in one real dimension. The Legendre transform does function a lot like that, but it works a little bit differently. So the goal of this video is to just work that out in some detail. Okay, so our goal is to take a function f that goes from R to R and to give it some mapping to a new function f bar that goes from some domain inside the real numbers back to the reals. Now let's start thinking about this pictorially. So let's draw a figure. It turns out that this particular function transform is going to be easiest to define for functions that are concave up. So we'll assume that we have a twice differentiable concave up function. So this is going to be our x-axis, and this will be our f-axis. This is the curve f of x. Now what we'd like to do is look at a line going through the origin that has slope p. So line p times x, since there's no y-intercept since it goes through the origin. The goal is going to be to try to find the point where the length of this blue line is maximized. Let's call that point x star. And then find the length of this line. Um, in fact, we actually want the negative of the length of this line. Okay. And since this depends on p, this will be our function f bar of p. How would we actually find this point x star? Well, I'll be able to show you without hopefully too much difficulty that we can look for the minimum over x of f of x minus px. And you may be doing a small double take right now. And then I told you we're trying to find where this blue line is longest. But notice that that point would be the maximum of px minus f of x. So it's totally identical to taking the minimum of f of x minus p of x. Sorry, minus p times x. So how would we typically do that? Well, we would use a first derivative condition. The first derivative condition that we'd want is we'd like for x star to satisfy f prime of x star is equal to p, or really f prime of x star minus p is equal to 0, which is precisely the same as f prime of x star is equal to p. Good. But how do we know that this is a minimum of this expression? The answer is that we need to take the second derivative. And hang on, let's back up for a second. Before we even do that, how do we know that this equation has a solution? Well, we don't. It may not. Here's a really good example. Imagine that we have a monotonically increasing concave up function. Since it's monotonically increasing, we simply don't have any solutions for p negative. But on some interval, we will have solutions. And so let's not worry about that for now. Let's simply find that we have a minimum at x star rather than a maximum. To do that, we'll want to take the second derivative and evaluate it at x star. So we want to first take the second derivative of this expression. But the second derivative of this expression is actually quite simple. It's going to be the second derivative of f of x. Again, we want to evaluate at x star. Minus the second derivative of a linear function. But the second derivative of a linear function is 0. So it's just this. And now we're in business. This has to be greater than 0 because f is concave up. Good. All right, so with all of that out of the way, we're ready to define the Legendre transform. So the Legendre transform OneNote really does not want to work today. Of f denoted f bar, is the function satisfying f bar of p is equal to the minimum over x of f of x minus x times p. Good. So this may exist even if f of x is not concave up, but let's focus on that for now just because we know that it will exist sometimes. In particular, it's probably a good time to figure out what that domain is. So if the image of f prime is equal to some interval a, b, then we have a solution to f prime of x star is equal to p for every point in a, b. And not only that, because the second derivative is positive, then we have a unique solution for every p to f prime of x star is equal to p. So that means that f bar goes precisely from AB to R. Excellent. The next thing to worry about is the invertibility of this transform. Again, to use the Fourier transform as an analogy, a nice thing about the Fourier transform is that we can take a function in, for instance, time space, transform it into period space, do so whatever manipulations we want with it, and then transform it back into time space at the end. We might hope that the Legendre transform has something similar. And in fact, it does. So the inverse Legendre transform let's say of G, denoted G bar. So I'm going to abuse notation a little bit here and just have bar mean either the transform or its inverse, is the function satisfying G bar, which is now going to be a function of x, is equal to the maximum over p of of G of p plus px. Just for consistency, let me say px here as well. Wonderful. Now, the hardest proof that we're going to do today is the proof that this really is the inverse of the Legendre transform. So let's do it without further ado. So maybe I should say, want to show f double prime of x is equal to f of x. Okay. The first thing to do is just to note that f double prime of x is equal to f prime of p star, which now we're going to think of as a function of x, plus p star as a function of x times x. And p star must be a function of x because as we change x, this maximum point must also change. Or similarly for the non-inverse transform, as we change p, as we change the slope, then this point will also change. Good. Okay, so we have that f double prime of x is equal to f double bar of x is equal to f bar of p star of x plus p star of x times x. And let's do that one more time so we can expand this term now. We'll get that f of x star of p star of x, 1, 2, 3, 1, 2, 3, there we go, minus p star of x times x star of p star of x plus p star of x times x is equal to the left-hand side. So just to clarify where things are coming from, this blue thing is giving us all of these terms as I just expand the Legendre transform by its definition. There we go. and then this stuff I'm just pulling down. All right, now let's group things a little bit since we have a p star of x here and a p star of x here. We'll get f of x star of p star of x, 1, 2, 3, 1, 2, 3, plus, let's say, p star of x, there we go, x minus x star of p star of x is equal to f double bar of x. Now we want for this to equal f of x. And this is true certainly if x star of p star of x is equal to x. So let's show that. So if x star of p star of x is equal to x, then we get the above is equal to f of x plus p star of x times x minus x. That's that x, and this goes to f of x, which is just f of x. So we're good. So what remains to show maybe it remains to be shown, is this point, that x is equal to x star of p star of x. All right. Now to do this, we're going to look at the object f bar prime of p star of x in a couple of different ways. The first thing to do is simply look at f double bar, of x, which we know is the maximum over p of f bar of p plus px. And how would we find this maximum point, p star? Well, we would just use our first derivative condition. So we would get that f bar prime of p star of x is equal to, well, it's just minus x. Good. So this is going to be one of the conditions that we need. For the other one, unfortunately, we're going to have to work a lot harder. We're going to do something similar to this. So we know that f bar of p is equal to f of x star of p minus p times x star of p. And that's just by the definition of x star. Good. Now, let's take a derivative with respect to p of both sides. That will give us f bar prime of p is equal to f, well, we'll have to use the chain rule on this term. Let me actually mark that down. And then we'll need to use the product rule on this term. So let's get to it. Here we have f prime at x star of p times x star prime at p. All right, then for the second term, well, for the first part of the product rule, we'll take the derivative of p with respect to p, which is 1, so we just get x star of p, and then minus px star prime of p. All right, and then given that we have an x star prime here and an x star prime here, we can regroup those. So f prime x star of p minus p times x star prime of p minus x star of p. All right, good. Now the key here is just to remember what x star means. So let's do that in a little marginal note. So x star of p satisfies that it's the point minimizing uh, f of x minus px. Okay, but that means that f prime of x star of p is equal to p. And if you look at this expression and then look at this expression, you'll note that this must be 0. So this implies that f bar prime of p is equal to minus x, oops, x star of p. All we need to do is now stick in for the value of p, p star of x. So we get f bar prime of p star of x is equal to minus x star of p star of x. All right, and this will be our condition 2. All right, now combining conditions 1 and 2, we get that minus x is equal to minus x star of p star of x, or x is equal to x star of p star of x, which is exactly what we wanted. And that completes the proof that f double bar of x is equal to f of x. Okay, that was quite an involved proof, and I don't expect that you should be able to remember it, but I did at least want you to see that this is a very well-defined function transform, at least for the class of concave up functions that we've talked about so far. All right, now that we've done all of this algebra, we should probably jump to some examples. There are a couple that I want to make sure that we do. The first is let's let f of x just equal ax squared. So we just want an upward facing parabola, and let's not even worry about linear and constant terms. Okay, the first thing that we should do is find x star. So x star again satisfies that f prime of x star is equal to minus p. Sorry, is equal to plus p. But notice that f prime for this function f of x is 2ax. So 2ax star is equal to p, which implies that x star is equal to p over 2a. Good. So now f bar of p is equal to f of x minus p times x. And minus f of x star, f of x star minus p times x star. Okay, well, f of x star is a times p over 2a squared. And then I want to subtract p times x star, so that's p times p over 2a. All right, we do a little bit of algebra. We get p squared over 4a squared times a, so just p squared over 4a minus p squared over 2a, which is minus p squared over 4a. Okay, so the important thing to notice here is that we get a downward facing parabola. And this will generally be true. If we had a concave up function, then its Legendre transform will be a concave down function. I think a good exercise would be to convince yourself that f double bar of x is equal to f of x once again. So here, that was one example. Let's do another example. Another popular concave up function would be some sort of exponential. All right, so let's do f of x is equal to a e to the bx. Okay, and just right off the bat, let's find f prime of x, which is ab times e to the bx. So now let's find x star. Well, x star satisfies f prime of x star is equal to p, and that would imply that a b e to the bx star is equal to p. So we're going to need to start moving some things around. We'll get bx star is equal to p over ab, and then we need to take the log. So I guess I'll just erase like this, log p over ab. And finally, we get that x star is equal to b inverse log of p over ab. Okay. Now to find f bar of p, we need to stick back in our value of x star that we just found. So it's f of x star minus px star. Okay, well, f of x star, actually let's move that up a little bit, is going to be a e to the b times b inverse log of p over ab. And then our minus px star will be minus p, and let's say minus p over b, log of p over ab. Okay, we see that the b's cancel here, and we get a e to the log p over ab. When we cancel this down, the e and the log cancel. We'll just get a times p over ab, which is just p over b. So we get p over b minus p over b log p over ab, or p over b times 1 minus log p over ab. And that's about all that we can do in this example. But once again, notice that this is going to be a concave down function. Okay, I want to do one more thing, which is look at an example that's more closely related to classical thermodynamics. And on the way, we'll be able to look at some properties. All right, so let's write the Sackur-Tetroda equation for the ideal gas. So we get S as a function of U V N is equal to N KB log sigma V over N U over N to the 3 halves. I'm not sure if I said this, but let's think about the monatomic case, times 5 halves N KB. And let's rearrange this to solve for U of SVN. Okay, so to do that, we'll take everything that isn't in the log and shuffle it around. So we'll get S over NKB minus 5 halves is equal to this log. Now we can exponentiate both sides and then start dividing things around. So we'll get that U over N to the power of 3 halves is equal to sigma inverse N over V times E to the S over NKB minus 5 halves. A couple more steps. We need to take U by itself and then multiply everything, or sorry, raise everything to the 2/3 power on the other side, then multiply by N. So we'll get N sigma to the minus 2/3, N to the 2/3 over V to the 2/3, E to the 2/3 S over NKB minus 5/3. And one last little thing is just to combine these powers of N on the right-hand side. So U is equal to sigma to the minus 2/3, N to the positive 5/3 over V to the 2/3, e to the 2/3 s over nkb minus 5/3. Wow, was that a lot of work. But let's start rearranging this. So we'll get that u is equal to some constant a, which here is going to be equal to, and I shouldn't say constant, but some quantity a, which is sigma to the minus 2/3 n to the 5/3 over v to the 2/3 times e to the minus 5/3, okay, times e to the 2/3, sorry, let's say e to the b times s, where b is now equal to, um, what will it be? 2/3 times 1 over n kb. And would you look at that? We've actually turned this equation for u as a function of s for fixed v and n into exactly the form that we had right here. So we already know if we wanted to Legendre transform u as a function of s, we could get u bar as a function of some other variable. Let me call it lowercase t for a second. And we know what that would be. So this is actually sort of an abusive notation, right? U of s is just some real and u bar of t is some real, but I think you know what I mean. So u bar of t would be exactly equal to what we got right here. P over b times 1 minus log p over ab. So we know what b is here. So our p is replaced by a little t. So t over 2/3 1 over nkb, and then 1 minus log of p over ab. And so p again is replaced by a little t over ab. So a is all this stuff. And then b is, what is it? 2/3 1 over nkb. Wonderful. And something sort of interesting happens. At least we get 3/2 nkbt times 1 minus log of a bunch of stuff times nkbt. All right. And this is somewhat interesting. Notice that u bar of t, where t is still our lowercase here, is equal to u of s star minus little t times s star. Now, what we often want to do in classical thermo is think of the Legendre transformed function as being extensive if the input function was extensive. So if this was extensive, then this should be extensive. And what does that require? Well, since S is also extensive, the only way that this is possible is if this little t is intensive. So let me now state that as a result. If the input variable to a function is extensive, then the input variable to The Legendre transform is, actually, let me say, called its conjugate variable is intensive. And we'll get much closer to why this would be helpful to us in future videos. For now, all I wanted to point out is that you should think that it's somewhat suspicious that we almost got the energy of the ideal gas here with some extra stuff added on. I'm realizing I missed a parenthesis here. So something odd is going on. We are finding something else that has type energy, but is not quite the energy that we're familiar with, the internal energy. In fact, we'll see in the next video that this is the free energy. This video has gone on quite a long time, and I don't mean to suggest that being able to do this algebra is super important to the subject at this point. But as we move forward conceptually, it's important to remember that the Legendre transform really undergirds everything that's going on. So with that, I'll say thank you so much for watching. And in the next video, we're going to start looking at free energies. I'll see you then.